Hey there, folks. So, uh, several people, a handful of people, asked whether my talk at Tilburg had been recorded, and unfortunately, it wasn't. So I figured I'd just throw together a quick recording, go through the slides, throw it up on YouTube, and then people can watch the talk. Also gives me an opportunity to talk about some work that some of the stuff here, there's some preprints to point to, but some of it there's no paper. And so I think it actually might be nice to have a video. Let's see if I can advance the slides. There we go. Okay, so anyone who has listened to me give a talk before, or read any of my papers, has followed any of the work from my lab, probably already knows this, but just to cover this up front, everything I'm going to be talking about here comes from ideographic data. So when you're dealing with ideographic data structures, nothing's different than a classic data set. You still got rows and columns. But the thing that is different is that those rows are time points instead of people. And then in terms of having multiple people, as the image here shows, you're going to think in terms of having multiple sheets of data, right? So every person has their own sheet with rows and columns, and then multiple sheets per person. And then, if it's not an idea you're accustomed to, it's not something I can give time to talking about here, but certainly some of my papers talk about it, and I can talk about it offline, exactly how you handle that. You need to basically have pipelines in R or whatever you're working with, and kind of apply your analyses across people and have ways of aggregating that and dealing with that. I'll allude to some of that here, but for the most part, those details are going to get left out today. Okay, so this talk was written for a keynote for the Tilburg Emotion Conference. And I wanted to take advantage of that to talk about some ideas that I've had over the last few years, and to try to kind of put it together as a pitch, really more than anything, for why discrete data is kind of awesome, and there's all sorts of things you can do with it. But usually what happens when you talk about discrete data is people don't like the idea, and you tend to get a negative reaction, tend to get some pushback from folks. And the most common thing that, at least for me, that I'm pretty sure that I hear, is this idea of lost information, right? So if you, and so normally the idea is there's a conceptualization that something's been captured continuously, and then you're going to cut it up. And really, I think the association is median split, right? So I have a good friend who may or may not watch this, and you may or may not have seen this person make comments to this effect online, who says every time I talk about this stuff that all they can think about is median splits. And I think that that's fair. I think that there's, we have kind of a hangover in our field from decades of people wanting to look at interaction effects in ANOVA and regression, and you want to have a high group and a low group and things like that. And so you split your data up, and I think the median for a long time seemed like an appealing way to do that. In the next slide, I'll show you a figure that I think makes it pretty clear. You just shouldn't do that. you just should never. It's just a bad idea. It's an arbitrary division point, and it's not the way you should break up your data. Now, I'm getting a little bit ahead of myself. I think this is in a couple bullet points, but I would like to advocate for us measuring things discretely. But even short of that, we can take continuous data and we can think of ways to discretize it, to make it discrete. But we do, we want to think of whether the divisions we create are meaningful in some way, theoretically meaningful, statistically meaningful. Is our data stratified? Is it clustered? The median doesn't tend to give us that, right? But these are things that we can look for. We can look for multimodality and stratification, and I think that we can take advantage of that to discretize our data. So here's a couple of data sets from my lab. I won't bother describing the study because I'm not going to otherwise get into this study in these slides. But we were measuring continuous anxiety here from the folks in this study. And here's two really nice, clear cases, two separate people, right? So participant 91 on the left, participant 85 on the right. And these are two clear cases where we do have bimodality. I think these are data that really can be nicely discretized. You could, there's, kind of activation, deactivation, on off patterns that we're looking at here. But neither the mean nor the median would give us that. So the means in blue here and the medians in red, right? So we could have come to this through visual inspection. I think both of these are cases where you could eyeball this and say, okay, here's where the upper distribution is, here's where the lower distribution is, but that's not the best approach if we're going to be working with data at scale. So we want to be able to do this with machines, with statistics, but just as a visualization, entirely possible. I think there are cases where we can measure something continuously, but very reasonably create discrete representations out of it. Okay, so what can you do other than a median split? Well, you can do a lot of things. The stuff that I tend to focus on has to do with unsupervised clustering. And so I'm going to talk about finite mixture modeling in these slides, but you can use k-means clustering, which is a distance-based clustering approach. There are density-based clustering approaches. So there's dbScan, optics, HDBScan. There's actually a bunch of these. There's all sorts of cool stuff out there. And all of it's in R, and it's fun to play with. And then, of course, this was the point I already made. You can measure your data discretely. So I'll show you some of that today. I'm a big fan of that these days. And that's another thing that I tend to get a lot of pushback on. I think a few things here. I think that, first of all, we can measure things discretely. I think you can, you can reflect on whether you're hungry or not, whether you're sad or not, whether you're angry or not. Now, but you might say there's also differences of degree there, and I kind of have at least two responses. One is I think we can capture those qualitatively, actually. So for instance, hunger, you can think of a degree of hunger in which you don't have to go get something to eat. You're hungry. Yes, you can identify that you're hungry, but you can also tolerate it. And then there's a degree of hunger in which you feel compelled to eat. And you can think of that as sets of information. I'm going to talk about sets in a little bit. You can think of hunger that's tolerable is either a set that's just hunger, and the degree to which you need to go get something to eat is absent. You can think of that explicitly as a set of two of hunger present, behavioral compulsion or behavioral intention absent. We don't have to get into those kind of details, but you can think of it in terms of, in an inventory of the qualitative details of the state of being. Then when you are so hungry that you feel compelled to get something to eat, that's a set of at least two: hunger and compelled to eat, right? So, and I think that if you can kind of get your mind around thinking in that way in terms of, deconstructing what we think of as severity into qualitative units, it actually works pretty nicely. Now, it doesn't work in all cases, and I think that there's examples. Pain's probably the one that comes to mind most easily for me. Things that maybe do make more sense as just more or less. But something I would say there is the other thought I have on this is that I have a conviction. I have it's conjecture. I don't think I have a ton of data to support this. I have some. We've looked at this a little bit, but I think presence absence is primary and degree is secondary. I really do. I think that we can capture quite a bit of information if we're willing to let ourselves try. We can capture quite a bit of information with presence and absence. I'll show you some evidence to that effect. Not that I won't show you any evidence necessarily that it's better than continuous ratings or that kind of thing, but I'll show you some evidence for how cool and how interesting and informative capturing things discretely can be. So yeah, so we already do this for a lot of stuff. There's plenty of examples of things that we dummy code or measure discretely. And I'm just kind of here to make the argument that we could do it with more stuff. And I think it just requires a little bit of a mental rotation and how we think about our data, how we think about our systems of measurement, but entirely possible. If NIH and NSF came out tomorrow and said, yeah, it's an absurd example, but if they said, oh, every single dollar we give out from here on out is only going to be given to science with discrete measurement, I'm sure we'd all figure out how to make it work. Okay, so one of the advantages to doing this is to represent compound information, this and this and this. Now we do that with other approaches. We do that with clustering approaches. I'm going to put that all together, in fact, in the next few slides. We do that with factor models. I think that what I'm going to show you here is a really nice way to think about this, mixing multiple phenomenological variables together, right? Thoughts and feelings and things like that. And when we're doing this ideographically, so of course, as I mentioned at the top, when you're working ideographically, your observations are time points rather than people. And then thus, if you're going to look at discrete information in a given epoch, in a given measurement interval in an ideographic time series, now we really are talking about states. We're talking about compound conditional information about what's going on in that moment of time. So these are discrete states and discrete moments. And that actually, again, this concern of lost information, this concern of, well, that's not how linear models work. And that's not how we measure our data. Our data are dimensional, our data are continuous. Overlooks the advantages that you can get out of discrete representations, which is what is happening right now and what exactly is it that's happening, which is a level of detail and a level of actionability and leverage that we really don't have with most of our approaches. To the point about dimensionality and continuousness and capturing dynamics, I don't think we're ever really capturing the true granular processes that we think exist, the true data generating processes. I think that should be acknowledged. But then also this idea of discreteness and understanding what's happening in a moment in time. I think I like to think of it like a snapshot, right? So if you have the example I've been using, although it really dates me, and some of you who are younger might not know what I'm talking about, but there's a very famous photograph of Michael Jordan. It's 1986 or 1987, I think, maybe 88. It's somewhere there in the mid to late 80s. He's in the dunk contest. He won the dunk contest with a dunk from the free throw line. And there's this very famous photo with ball kind of cocked above his shoulder, just kind of floating through the air mid jump from the free throw line. Nobody looks at that photo and thinks that Michael Jordan is levitating, right? We know that this is a snapshot of a larger dynamic process, that he has run across the court, leapt from the free throw line, that he's currently flying through the air and he's about to dunk the basketball. We see the people in the background. We know that they're there, they're alive, they're watching, they're about to clap. Like all of that information is available to us in this snapshot of what's going on, right? So something else that I'll talk about here is that we can also encode sequences across measurement intervals, right? In a nice kind of direct manner, that this happened and then this and then this. We tend to, even when we're working ideographically, even when we're working in a time series framework, we tend to collapse across time. Like we measure things like autoregressions and vector autoregressions, where we say this variable predicts itself on average from moment to moment, or this variable predicts this variable. Again, we're forced into linearity. We're in linear models. We're kind of smushing across time rather than saying, well, this happened in this specific moment and it was followed by this event in this specific moment, which I think, again, gives us a lot more agency, a lot more actionability as researchers and clinicians. Yeah. And so another piece, and I'm kind of getting into stuff that I don't really unpack in this talk, but then I had another talk, and maybe I'll make a video of that one as well, where I really unpack a recent paper that I have under review, where we talk about sets and set theory, and in a larger context of necessity and sufficiency. There's this idea of minimizing assumptions that, I'm really putting the cart in front of the horse. I haven't really introduced the idea of sets, and I will in a moment. But when we're thinking in terms of sets, all we're encoding is presence and absence and sequence, and that's literally it. And we'll do that with some Boolean operators, some dichotomous coding. So all of the assumptions and the requirements that you have from some of these other models, vector autoregressive models, even Markov models, we don't have to worry about those, that the interval lengths are equivalent, for instance, or what the time scale was. We can kind of do away with these things to our advantage. All right, so here's the idea of sets. Again, apologies for kind of talking about this before really introducing the idea. So set is just a collection of objects. And in the current example, we're going to use this as a way to specify compound events, right? So A and B and C in a given unit in time, that's set A, B, C, right? So we're going to think about building sets with a mutual information algorithm that Nicholas Leenertz and I have created that's available on OSF. I'll give you a QR code in a moment for the paper that comes from that gives you much, much more detail. I'm just going to briefly touch on that here. And then I'll also show you some stuff thinking about set construction using finite mixture modeling. And then regardless of how we do this, our sets, we're going to think of them this way, right? That there are different conditions that are present. And if those conditions are present, we're just going to use simple if-else rules. And represent our sets as dummy codes, right? So if condition A and condition B and condition C are all present, then we give set ABC a 1. Otherwise, we give it a 0, right? So it's just a new variable. It's a very simple dummy code. It's present absent. But what it does is it's a nice data compression tool because we're taking this total conditional information and we're compressing it into this dichotomous variable. So today we're going to be talking about combinations. These are, just to focus on that for a second, where these are concurrent conditions, right? So this is time series data, literally measured in time. We're going to be thinking about things that are concurrent across a row of data, meaning these are things that go together in time. So it's a little bit different conceptualization than covariation. So instead of thinking of covariance, we're thinking of concurrence, just that these things co-occur in time. We can also think in terms of permutations. So for a combination, the order doesn't matter. For permutation, the order does matter. So this gets us into sequences of events or conditions. And then there's this idea of transparency, right? So once we encode these as dichotomous variables, again, all that variable reflects is the presence or absence, possibly sequence, of the conditions we're talking about. There's no factor loadings, there's no weights or coefficients. It's just simply presence, absence, sequence. And so there's a very direct kind of relationship between what the information is conveying and the world that we see and observe and experience. Just a little visualization of these ideas for you. Hat tip to the website Seeing Theory for these figures. So if we have 4 possible inputs, we're going to have 4 potential sets of 1, 6 potential sets of 2, 4 sets of 3, 1 set of 4. And that's, again, a combination where the order doesn't matter. But then when sequence does matter, we can see that the complexity blows up on us pretty quickly. This is just with 4 inputs. And then as you go to 5 and 6 and 7 and so on, it becomes a larger and larger inflation of the total possible information. So I've mentioned this already. There's this idea that I'm pretty focused on these days of actionable information. So when do things occur? How often do they occur? And for how long do they occur? Those are not things, just to give that just a little more treatment, that these are not things we really can easily extract from most of our models. One exception is a logistic regression model. That's not bad. I say a bit about that in the paper that I'll give you a QR code for in just a moment. I say more about that in this other talk that I mentioned a moment ago. I'm not going to say too much about it here, but I do want to acknowledge, because you might be thinking, oh, logistic regression can kind of do that, and absolutely. So it's not that there's nothing that we currently have that provides this. It's just that an explicit shift into discrete data makes this much more direct and accessible, because that's what you're modeling, and that's what the inferences are based on, and that's what the analyses tell you. That's the inference that's provided, right? When is it occurring? How often? For how long? And I think that there's a lot of that we can do with that, especially in terms of those of us who are clinical psychologists. You're thinking about, when is there a problem? When do I act? In what way do I act? What do I act with? These are some of the kind of core central questions of the work that we do. All right, something that I'm just going to give a quick coverage of, and then you can go read more about elsewhere. But there's some really cool work that is somewhat done, but also ongoing. These algorithms, we're literally improving them day by day. Nicholas and I have some versions posted on OSF. They work really nicely, but we are working on making them work faster, work better, be able to handle larger amounts of information. So these are still under construction, although the current versions work pretty nicely. So the algorithm here is one that uses mutual information to evaluate concurrence and build sets. So what we do is we feed it a data set of discrete information. In the present case, it will all be dichotomous variables, but it can handle more potential states than two. But we are going to just be talking about dichotomies here. So you're going to take a data set of dichotomous variables and give it to the algorithm. Algorithm is going to create all possible pairs of variables and assign them a mutual information value. I'm not going to be able to explain mutual information in detail to you here, but it is a correlation-like analysis that requires no assumptions of linearity, no assumptions of normality, and is really nice for evaluating concurrence in this way. We can also get a p-value out of a mutual information value by converting it first to a G statistic, and the G statistic is chi-square distributed, and then you can get a p-value. And so we can retain any pairs of variables that meet our p-value criterion, and we discard the ones that don't. And then what we're going to do is we're going to, as I mentioned earlier, we're going to recode like, for instance, the pair AB into the set AB. That's a new variable. We'll call it set AB. Every time A is present and B is present, that will get a 1. In all other cases, it gets a 0. And now we have our new dichotomous variable. We're going to take those new dichotomous doublets. We're going to pass them back through the algorithm and pair them with the original singles. And we're going to see if we have triples, right? Take the triples, pair them with the singles for quadruples, take the quadruples, pair them with the singles for quintuples. And we're going to do this until either we reach a level of complexity that we've pre-specified at the outset. So for instance, actually, I won't show you any sets greater than 5. So that was pre-specified, that it would stop after sets of 5. You can also just let it run however long it needs to run until there's no more sets that meet your p-value or mutual information criterion. So just a quick little visualization of this. I'm not going to I'm not going to get into any more detail about this, but I'll, as I've already mentioned a couple of times, I'll give you a QR code in just a moment. So these are some data from Sarah Victor's lab at Texas Tech. And this is an individual from her study who had a sad, hopeless pair, sad, ashamed pair, and a sad, hopeless, ashamed triple. So let me orient you to this table because I'm going to show you a bunch of these here and kind of help you understand what you're looking at. So again, this is that same individual from Sarah's data. And the variable that we're looking at is, I feel that life is not worth living. The marginal probability of that, the likelihood that that person felt that way was 0.59. So they felt that way fairly often. This first column are potential sets. And this person, we already saw that there's a single of sad, hopeless sad, ashamed, hopeless sad. And I want to point out that all of the values in these first 4 rows are identical because this person never felt sad without also feeling ashamed and hopeless. So all of those rows 1 through 4 all occurred. This is the marginal probability of the set. They all occurred 56% of the time. When they occurred, the conditional probability of I feel that life is not worth living was 0.95. And then something that I won't be getting into, but the paper talks about quite a bit, is entropy and conditional entropy. And basically this over here, right here, tells us that these 4 sets explain 60% of the information in I feel that life is not worth living. We also see some sets here, like for instance, angry all by itself, I would argue is necessary and sufficient for feeling that life is not worth living. It occurs 41% of the time, but when it does, this person always felt that life is not worth living. So this is just a little kind of introduction to this idea of both thinking about sets, our mutual information algorithm for constructing sets, and then also thinking about how you can use these sets as predictors for outcomes of interest. If all of this is interesting and exciting to you, by all means, take this QR code, go to our preprint, give it a read. Yeah, it's under review right now, and we'll see how it does with that process. Okay, so this is stuff I've been talking about now for a couple of years. So perhaps if you clicked on this video, you've already seen me talking about this, but if not, still, I think you can benefit from a little introduction. So finite mixture modeling, this is a way of trying to discretize our data when we're trying to do this with multiple variables at once. So the example up here, this is from Wikipedia, just an image of a bivariate normal distribution. So this is a case where there are not multiple latent classes or mixtures or components. These are somewhat synonymous words. And then on the bottom is some images that I snagged off of the internet, I guess having to do with volcanoes and volcano eruptions. And this is a case where there are 3 classes, and we can see that there are these density, spots of differential density in the multivariate distribution. And these images try to help you see that. The analysis tries to find these in a bottom-up data-driven kind of way. So we're going to start with one class. We're going to add a second class, a third class, a fourth class, and then we're going to try to kind of pick the best solution with something like a Bayesian information criterion. It is very important to mention that this is not an analysis. I really have to say, maybe this is opinion. I don't think this is opinion, though. This is not an analysis that quote unquote carves nature at its joints, right? So this is there's a lot of artistry to this. There's a lot of subjectivity to this. I think it is a tool. I think it's a very cool tool. I think it's more than cool. I think it's a very useful tool. I've been making use of it in a lot of different ways recently, but it is a part of a larger process. And I think if you're going to be using these models, I think you want to go into it at the outset, understanding that you're going to be bringing subjectivity to this, understanding that there are, it's a garden of forking paths. There's lots of different choices you can make. And I think that you want to build into your approach some sort of approach for evaluating where those different choices lead and whether they're effectively the same or different, and what that means. And there's a lot to consider here. And I just, I'm belaboring the point here, but I just think that this is something you don't want to think of as you feed your data in. You use the BAIC and you get an answer. I really don't think that that's how this works or how it should be approached. So speaking actually of that, speaking to that, we separate the idea of discovery from validation, and in fact have a second step in between those two, of what we call distillation. So the first panel here on the left is just helping you understand, again, returning to this idea of ideographic data structures, and now combining that with this concept of finite mixture modeling. There's Cattell's data box, which just helps us understand that data in behavioral sciences and human subject research is always a three-dimensional idea, right? So there's always people and variables, and I would say there's always time. Even things that are measured cross-sectionally, human beings exist in time. The things that we do, the things that we experience, the variables that measure our experience and functioning, whether you've measured them in time or not, they always do exist in time. So, yeah. Okay, so discovery is just that. We want to kind of maximize the total potential information that we're working with. So we do finite mixture modeling of every single person's individual data set, and we kind of do that in a very unrestricted way. Just let the BIC fit the models. The BIC very famously tends to overfit models. If you get into the primary literature on mixture modeling, that's something that comes up quite a bit. Useful tool, but it tends to over differentiate, to overfit and give you more classes or more components than you should. Again, subjectivity, there's no carving nature at its joints. So by doing it this way, and by just letting the models run kind of in an unrestricted way, and just automating the BIC as the metric for retaining classes, you tend to get a lot of classes. You get a lot of information back. So then what we're going to do is we're going to create a new data set that we're trying to visualize here, where the number of rows is the number of total classes across all participants, right? So if participant 1, right, so CL is for class, the first number is for the participant, the second number is for the class. If participant 1 had 2 classes, row 1 are the values, the average values, the mean values for participant 1's class 1. Row 2 are the values for participant 1's class 2. Here we see participant 2 had 3 classes, right? And there are those, and so on and so forth. So again, we're going to create a new data set where the values are the mean values for each variable, for each class, for each individual. And then the rows are 1 row per class for all individuals. So we get a pretty big data set that we're now going to do a second mixture model. We're going to cluster our clusters, right? And then we get what we've been talking about as archetypal states. The paper that this comes from got some pretty pointed reviews back, and I don't think the 3 folks who read it, or at least 2 of them, didn't have the most positive reaction to that. So there's a major revision going on right now, and some of the language is shifting. The reason we may or may not stick with archetypal, the reason why the word archetypal was chosen is because what you get back is really neither ideographic nor nomothetic. You get something that is shared across individuals, but we then use and functions very nicely at the individual level, right? So that's this idea of archetypal, just something that kind of represents an idealization, but still just an approximation of the idealization. Sorry, that's a lot of syllables. So that's the idea. Whether we stick with those words or not, we'll see. Finally, I'm going to gloss over some things here because there's a lot of details, and I think it would take more time than I want to put into this right now. But we validate by you have to get out of the mixture models into into the space of out of sample data to validate, really, in my opinion. And so we have a process of selecting exemplars from the available time series in the training data. We use that exemplar to create a prediction model. That prediction model is then used to test holdout data, and we can see, how well these classes, and again, we recode these as dichotomies to keep coming back to that idea. So you're talking about a dichotomous variable that's encoding, in this case, 6 emotion variables. And then the question is, right, going all the way back to the beginning of the talk, are you losing information? And the answer is no, not really, not a ton. We retain a lot of that continuous information encoded in the dichotomy, and I'll show you that in a second. All right, so these are data taken from the How Nuts of the Dutch study. There were 838 total time series that we were working with. We split that up randomly into 500 training sets and 338 testing sets. And we do the discovery stage. We get a huge number. I can't remember off the top of my head, but we get a very large number of total ideographic classes. We cluster the clusters. We actually get many more than 7. I think it's 16. I don't recall that off the top of my head either. I guess maybe I could have refreshed my memory before I started recording this. But we then use something called an entropy plot to reduce it down to 7. Now, an entropy plot, I think the easiest way to explain it is it's very much like a scree plot. You're going to look at the reduction in entropy as you add or subtract, the changes in entropy as you add or subtract classes, and you're looking at it in the same way as a scree plot. And you're looking for, if this is coming through in the video, right, inflection points. So it's a visual analysis, and you're literally looking for bends in the line, and you're saying, okay, if I pick that bend, I'll get this many classes. And again, there is subjectivity to it. There is artistry to it. In this case, there was a 7-class solution. There was also a 4-class solution. And I went with 7. And then we built the whole paper up around 7. And we've stuck with 7. But there may be reasons to think that more parsimonious, that simpler solution, that 4-class solution, was the better choice. And I have a couple points where I'll elaborate on that as we go through the rest of this. But we went with 7. That's what went into the paper. That's what's still in the paper, even as we revise it now. We didn't want to really kind of monkey around with that too much, given that that was the choice that we made. So just trying to help you kind of understand everything that's going on here and how it all kind of fits together. So this is one individual's data. Now, we didn't otherwise aggregate the data in this way, but just for visual user friendliness, we've collapsed the 3 positive affect items and the 3 negative affect items into positive affect, negative affect, which you see here as the raw data. Red is for positive, blue is for negative. I'll come back to this in a second. So up here, this was the ideographic mixture model solution for this individual. They had 4 classes. And then now there were 7 potential classes, but not everybody had all 7. That's the common information. These are the archetypes that are available, right? But for most of the people in the sample, they had some subset of that. So for this individual, they had 4 ideographic classes, profiles, components, mixtures that mapped onto 3 of the pooled classes. So this person had 2 of their classes, class 1 and class 3, collapse into one pooled class, which was class 2. So they were 2 negative affect classes that were differentiated, if you see here, by the level of anxiety, and those were just collapsed into a negative affect class. So this person had 2 positive affect classes, one slightly higher, one slightly lower, and 1 negative affect class. Over here, what you're looking at is you've got the person level, the ideographic classes on the top bar, and then these are the pooled classes on the bottom bar, and then a handy-dandy little conversion chart that Gal Lazarus coded up very nicely. This is all Gal's handiwork, and it looks very nice. And this is just kind of trying to help you see how all of this kind of fits together, right? Just another example, this person had 6 classes at the ideographic level, but again, also only had 3 classes from the pooled classes. But here we have 1 positive affect, 1 negative affect, and an average level, right? And then, so in terms of these time series plots, what's really nice, and one of the reasons I'm recording this right now, even though maybe you can hear my voice, I have a little bit of a cold, but I was just having an exchange on Blue Sky with Tom Rodabaugh, talking about affect dynamics and some of the problems with those operationalizations. And I was saying, oh, I have some alternatives, and so and this is that. These are those. I think that we can think about things like inertia and stability, instability with these types of plots. By looking at onset, offset, duration, and frequency, and the variability of the changes in the states. I think this is a nicer, more direct way to look at this idea of affect dynamics, at least insofar as especially variability, instability, and inertia. Certainly inertia, because it's something that I've said several times. I said it today online, is that I think there's a couple problems with the inertia operationalization, but the one that really stands out to me more than any other is that in the case that you have maximum inertia, right, the variable is absolutely not changing because it has maximum inertia. I don't know, no alternative way to phrase that. Then the autoregression's undefined. You basically get that there's no inertia because you get no estimate. Whereas the true situation is that it's maximally inertial. Is that the word? I'm going to go ahead with that. All right. So just a couple things I want to just real quick show you and then move on, that these estimates are fairly consistent. So remember, we had that 500 person training set, the 338 testing set. We did all of these steps in both, right? Discovery, distillation, and then this is part of our validation, being like, how well do the two agree? And the answer is pretty nicely. Not perfectly, not like exactly, but pretty darn closely. These line up pretty nicely. We then take them and do a nearest neighbors, and you say, well, if you were assigned class 1 in the training set, would you have been assigned class 1 in the testing set, etc.? 41.5% of the time, it's an exact match. But what you can see, with the naked eye is most of the time when it wasn't an exact match, it was off by 1. So again, this point about the subjectivity inherent to this approach, the point about BIC and its kind of, the fact that it tends to overfit and it's really not this perfect way to quote unquote carve nature at its joints. And then the use of entropy plots. One of the things that I kind of take away from this analysis is, maybe we really should have, in looking at that entropy plot, we took that first inflection point, but we could have taken the next inflection point that told us, you could get away with just 4 classes. And in fact, in the data that I'm going to show you next, that's exactly the choice I make as a result of having gone through this study and kind of, trying to learn from, past choices and those outcomes. Nevertheless, just a moment. Nevertheless, again, we do this. We have the 500 training. We have the 338 holdout. So we don't touch those holdout. Now, a moment ago, I showed you that we did the nearest neighbors. We did, and kind of map the two solutions on top of each other. But then we didn't otherwise use the finite mixture model solution in the testing set. We just literally threw that away. So now you've got these time series. They're otherwise untouched. They're held out, right? And you really can, I think of them as if they were new data coming in real time, right? So you fit your models, you've got your prediction model, and now you're going to pass these new data through the prediction model to generate these dichotomous variables, right? So we've got this continuous stream of data, the 6 input, I just did this for 6, the 6 input variables are passing through our prediction model, and we're going to populate 1s and 0s for the different classes into the time series. And then the question is, right, going back to the very beginning of this talk and the concern about discretization, are we losing information? The answer is absolutely yes. but not nearly as much as you might worry. We're retaining. So here's two of the variables, gloom and cheerfulness. So this is kind of a central NA variable and central PA variable. And these are translations from Dutch words. You can see that we're getting about 50% of the information, right? So we're not losing that much, really. We're retaining, and again, just to reiterate this is a dichotomous variable that's encoding the fluctuations, the variability in 6 continuous variables, and then returning to us about half of the total continuous information. That's pretty darn good. And I would also argue, although I'm not going to elaborate on this very much here, but I'm happy to banter about it online with you. If you're on Blue Sky, ping me. If you're not, ping me by email, and I have some invite codes, and let's get that going even more than it already is. But yeah, I would argue, do we want or need the totality of the continuous information that's available to us in a given variable? Again, we're creating these stratifications, right? These activation, on off patterns for good mood, bad mood, right? PANA, and the stuff in the middle when someone's at their average, is that as informative? Do we care if we lose that? Maybe not so much, would be my position. Okay, so shifting now to some other data. These data, this does not have a preprint or a paper, but this is stuff we're actively working on right now. What I'm calling high resolution EMA. So these were data that were collected 24 times a day for 15 days, 24 times a day. So this was every half hour for these folks. And just really appreciative of the job that they did with giving us these really amazing data. We had more than 115 folks, but these are the folks with 80% completion or better. So we have really some wonderful, beautiful, nice, dense data from these people. One of the ways we got this kind of data collection was the EMA survey was really compact. So just 6 continuous emotions and 2 discrete emotions. And as I've already alluded to a couple times, this time, same exact process, procedure. We did discovery, we did distillation. After the distillation phase, in fact, because for these data, BIC tends to overfit, and that's, of course, unsurprisingly, a function of the sample size. We're talking about 300 to 400 observations for each time series here. So the BIC wanted even more classes. But the entropy plot was pretty consistent, actually, with what we found in the last study. And there was a 7 or 8 class solution that was suggested by the inflection points in the entropy plot, and then also a 4-class solution. And this time I went with the more parsimonious. And when I say 4, it's really actually closer to 3, because if you notice, class 3 here, it happened quite infrequently. It was in a minority of participants, and for those participants who had it, it happened relatively infrequently. So really, we're looking at class 1 being just kind of everything at the person's average, the person-specific average. Class 2 being a negative affect class, class 4 being a positive affect class, and class 3, excuse me, being this other negative affect class that was mostly punctuated by sadness, and less of a decrease in positive affect compared to class 2. Just another, peek at some of these images. I did these rather than Gal. They don't look as nice as Gal's, and I couldn't figure out why. So, but just, another hat tip to him, and revealing my own coding shortcomings. But one thing to point out is we're seeing a lot more state transitions, a lot more class transitions. This time, actually, the pooled classes are on the bottom. The pooled classes are on the top. They were on the bottom before. The idiographic classes are now on the bottom. but because the data were collected so densely every half hour, I think we have more opportunity for state transitions. And it brings up this question about, not a new question, and certainly not just a function of discrete measurement, something we think about with continuous models as well, of, the sampling frequency relating to what you can or can't derive from your data. And, something that I've been thinking about is kind of, a chaos theory kind of conceptualization, not insofar as doing any kind of mathematics connected to chaos theory, but the idea of self-similarity, right? And that if you can, for these data, for instance, something that would be pretty interesting to do with them is we've binned it in half-hour bins here, but we've got plenty of observations. We could shift that. We could look at half hour, hour and a half, 2 hour, 2.5, 3, right? And see if we see consistency in, the number of states we find, the transitions between states, the frequency of transitions, and possibly home in on the true pattern, by finding the resolution at which going into a smaller resolution doesn't give you any more actual granularity, and where you have self-similarity there, kind of repetition of pattern across levels might be a way to determine what the quote-unquote true level is. Just an idea, just a thought that I just will throw out there. But certainly, as you can see from comparing these images to the ones we just saw a few slides ago, by increasing the resolution, we do increase the opportunity for state transitions, and then we seem to get more state transitions. All right. So now, because these data were measured so densely, when you're looking at lags, and I'm going to be talking in just a moment about a kind of a different conceptualization of lags than you're probably used to. When you're looking at lags, you only have, ideally, you should only be looking at your intra-daily lags. You only have as many lags as you had within the day. I think most people agree with this who do this type of work, who do EMA work and time series work, that that evening observation is just different than nighttime observation. Or usually there isn't an observation, that nighttime period, the person is sleeping, and it's just a qualitatively different state of being. It's just a different thing. In the past, I have some papers that are published where we applied cubic spline interpolation and resampled over that period. I don't do that anymore, and I don't think I should have ever done that, because I don't think we should be treating the nighttime as qualitatively similar. But in this case, anyway, 24 observations per day give us 23 intradaily intervals, and really give us a lot of opportunity to look at, lag 1, lag 2, lag 3, lag 4. And I did that here. Now, again, if you do that in a VAR model or in a Markov model, that can get pretty messy on you pretty quickly. What we're doing is we're using sets here. So I created lags in my data, okay? But then I used my mutual information algorithm. So it's just looking for concurrence along a row. Well, when you have your data and you duplicate it and you lag it, and then you lag it and you lag it, and you look across a row, you've got your contemporaneous lag 1, lag 2, lag 3, lag 4 across a row. And the algorithm doesn't know that those are lags. It's just rows of data. It's going to look for these variables in the same way it did or does for any other variables. Now, again, these classes have been recoded as dichotomies. So what we're looking at across rows are zeros and ones, and we're looking at the presence or absence of these classes. And so what you're seeing here, for instance, is entirely related to class 2 for this individual. Now, if you remember at the top, I said that these folks gave us 6 continuous variables, and they gave us 2 discrete variables. So those were anger and fear. And so this person, they felt angry 17% of the time. And when they were currently in class 2 and had been a half an hour ago and had also been an hour ago. So class 2 lag 1, class 2 lag 2, that's a set. That occurred 10% of the time. Well, then the conditional probability of anger went from a marginal of 17% all the way up to 60%. So that's a 250% increase in the likelihood of feeling angry, right? And the odds ratio is nearly 11, and the p is going to be very, very small. And then all the rest of the sequences, I mean, they're combinations of sequences, and they all relate to class 2 and they're different kind of orderings and combinations of different lags. What I want to point out just briefly is contemporaneous effects they get overlooked a lot. Now, I'm not the first to talk about this. For instance, I know that Aidan Wright has a paper that he talks about, the value of contemporaneous effects. Or maybe he doesn't have a paper. He certainly talked about it on Twitter, but I believe there's a paper. Apologies. Maybe I'll figure out what I'm talking about and link it in the video description once I have this uploaded. Anyway, just trying to acknowledge, not the first person to say this. There's a lot of information in the contemporaneous effects. Sasha Epskamp's also written about this. I know that for a fact. He has a cool sprinkler example with aliens trying to figure out whether the sprinkler makes the lawn wet or the wet lawn makes the sprinkler go. Yeah, just a good point about how the information can be embedded in a contemporaneous relationship. Anyways, we tend to overlook these, though. These other examples aside, people love the lagged information, that directional information. But one of the knocks against contemporaneous information is it's just a correlation, and it tends to have a stronger relationship, and you don't know the direction and all this kind of stuff. But I just want to point out, and it's taken me a little bit longer than it probably needed to, but the contemporaneous effect of being in class 2 in this moment, predicting being angry in this moment, was strong. The conditional probability is 0.49. But that's 11% lower than this sequential information, right? So we're getting quite a bit more bang for our buck out of thinking about these sequences. It's not just that I'm in a bad mood right now. It's that I'm in a bad mood right now. I was a half an hour ago, and I was an hour ago. I've been in a bad mood continuously for the past hour plus, and now I'm feeling angry, right? And that's the strongest predictor of this person's likelihood to feel angry. Here's another participant, and now we're looking at their responses about feeling afraid, which they felt 32% of the time. Now, I did say that class 3 didn't tend to show up very often, but for this person, it showed up 10% of the time on its own. Interestingly, so, if you are contemporaneously in class 3, for this person, they were always feeling afraid. So kind of a necessary and sufficient condition for feeling afraid. But other, the class 3 really kind of promoted fear for this person, even if, here the second strongest predictor is lag 2. So even if they were feeling this way an hour ago and then had kind of transitioned out of that state, they're still very, very likely to feel afraid an hour later. So that's interesting. So there's other interesting stuff to unpack here. Here we have class 2. So the other negative affect state has an effect. But I want to look at this for a moment, because you see these percentage changes are in the opposite direction. And we see these conditional probabilities are very small. And look at the protective effect of the positive affect class. And the most potent protective effect was being in a positive affect state now, having been in one a half an hour ago, and having been in one an hour ago. So an hour plus of sustained positive affect, which for this person happened 20% of the time, reduces their likelihood of feeling afraid by 82%, which is really nice. There's this really protective effect of positive affect. Again, we see different combinations of lag structures for class 4. And again, just being in a positive mood by itself, fairly protective, but not as protective by a margin of 12%, not as protective as this sequence of positive affect now, half an hour ago, and an hour ago. All right, so we want to take this sequence idea and push it a little bit further. And in order to push it a little bit further, we're going to keep using the tools we've already been using. So that's thinking about data discretely, using sets. But now on top of that, what we want to throw in is an EMA survey that itself has a temporal structure to it, so that we can dig a little bit deeper into this idea of sequence. Here, I'm just going to show you one data set. This is a pilot. Yeah, we did a pilot series. So this is just one. So we did, I think, 6 or 7 of these to prepare for a study that we're running in our lab now, which again, it has to do with this sequential structuring in an EMA survey. It relates to emotion regulation and emotion regulation approaches and whether they were used or not. So some things have changed. Actually, we learned a lot, as one does from a pilot study. So there are things in this that have changed in the ongoing study, but there's still some really cool data here. So in this case, for this individual, they were given a checklist of 10 negative emotions and asked if they'd experienced any of them. If they said yes, in response to saying yes to that, they were asked whether they felt compelled or motivated to respond to the emotion or act on the emotion. This is this idea of urgency. We did not use the word urgency in this prompt for the yes/no. But then if they said yes, then we did use the word urgency. Then we said rate the degree of urgency you felt in response to the emotion. To what degree did you express? So those were both continuously measured. Then we said, did you feel motivated or intend to regulate or change your emotion? Yes or no. How much did you try? To what degree did you feel you could be successful? To what degree was your attempt successful? And then finally, we asked them if they are currently distressed. Here's a visualization of the data for this individual. This is an icing model. So it looks like a regular old network model, but it's a network model for dichotomous data. We get this nice sequential structure. So here are the negative emotions, and then the urge to respond to them, and then the motivation to change the emotion or regulate the emotion. So the icing model is able to very nicely. It doesn't have directional arrows, but we know those paths are sequential because of the way we ask the questions. We also have some kind of more distal emotions and more proximal emotions, and I'll make use of those in just a moment. So, okay, so we're going to look at 3 outcomes here. We're going to look at the urge to respond to the emotion, yes or no. We're going to look at the motivation to regulate or change the emotion, yes or no, and then we'll look at whether the person was currently distressed. So for that first item, urge to respond to the emotion, this was a feeling or an experience they had 34% of the time. And we see different combinations of agitation, frustration, anger, and fear that are all pretty potent predictors, ranging from conditional probabilities of 67% to 73%. All around 100% of an increase in likelihood. So these are all pretty good, strong predictors. But again, getting back to this point of compound emotions, we do see agitation on its own having a pretty strong effect. But for the most part, we're seeing that the strongest effects are compound emotional experiences, the strongest of them being fear, agitation, and anger, or fear, agitation, anger with frustration. Those occurred at almost the exact same rate. You can see that there's some differences over here that you don't see here because of rounding. There were differences here. They weren't exactly matched, but when we round to 2 decimals, they look that way. So again, agitation, right? The most proximal to the urge to respond was the only variable that had an influence on its own. And otherwise, it tended to be paired with fear, frustration, and anger. Okay, embarrassment was not in those top predictive sets. Now we're looking at that next step down, that motivation to regulate emotion. And here we see this gating effect of urgency. The strongest predictor is whether there was urgency or not, because that was the thing that immediately preceded the potential motivation to regulate emotion. So Motivation to regulate was present 32% of the time. When there was an urgent need to respond to the emotion, then they wanted to motivate they were motivated to regulate their emotion 80% of the time. The rest of the predictors are different, again, combinations of these emotional experiences, but none of them are even within 10% of the strongest effect, which again is just this urgency. And so just to keep refreshing the image here, right? So the emotions are distal to motivation. Its most proximal predictor is the urge to respond to the emotion. And we see that is the strongest predictor across our sets. So let's unpack this in terms of this kind of distal to proximal progression, this sequential progression. So actually, let me just click back here. So remember, embarrassment is the most distal emotion. And when we put embarrassment in by itself, predicting motivation to regulate, it's significant. We get a nice p-value pretty much right at 0.001. Z-value of 3.32. So this is the most distal variable. Now, anger and frustration I would still call distal, but they're slightly more proximal to the target here. We add those in, and we see that embarrassment is no longer significant. It's now P is right at 0.05, and the other two are significant. Okay. So now the next step in, the next most proximal step, was agitation and fear. So now we add agitation and fear, and now we see anger, frustration, embarrassment, all now non-significant. And then finally, that last step, the most proximal variable to the motivation to regulate, was urgency. And when we put that in, when there was an urgent need to respond to the emotion, all other variables are now non-significant. So we have mediation. Now, I speak out against mediation often. I'm not a big fan of mediation. I don't like the idea of a mediation model, and you put variables in a mediation model and it's supposed to tell you something mechanistic. But we have a different situation here. So the data had an explicit temporal sequencing in the way we collected them and the way we asked about the variables and the logic structure of the survey itself. The variables also were, again, dichotomous. They were discrete. They were 0, 1. So what we can think of is we can think of this progression from distal to proximal like relays, right? Like electrical circuits. So I'm stealing this idea from Claude Shannon, which I've stolen quite a number of ideas from recently. So the paper that the QR code was for earlier takes you to a whole discussion of entropy and conditional entropy and information theory. And I think Claude Shannon has a lot to offer our field, even though it may not seem that way on the surface. And one of the ways that he thought about encoding information was in bits, dichotomous representations, 0 and 1, and then thinking of those bits like relays. He was an engineer, and so that was a natural way for him to think. And I think it's a nice way to think about these data. All of the other variables are mediated by urgency, not because I've used a mediation model. I haven't. This is just a logistic regression model. But the data are 0, 1, and they have an explicit sequential order. And that most proximal variable to the dependent variable is like a gating mechanism. And so therefore, that is what's going to carry all of the predictive information, because when urgency was present, the emotions are ungated and they can influence the motivation to regulate. When urgency was not present, the emotions, even if they had been present, have no effect on the motivation to regulate. Okay. So then finally we ask, are you currently experiencing distress? This person was experiencing distress 35% of the time. And something I want to point out here is all of the top predictors, which are all yielding conditional probabilities of 0.95. So making the experience of distress a near certainty. All of them either contain the urgency indicator, the fact that there was an urgent impulse to respond to the emotion, or the motivation to regulate. So I don't talk about it much in this set of slides in this talk, but again, it's kind of the general framework that the paper with the mutual information algorithm and the conditional entropy stuff and that the QR code takes you to. The general framework is one of necessity and sufficiency, and trying to think about sets of variables as being composed of necessary conditions and then sets becoming sufficient to predict the outcome. So in this case, I would say all of these sets are sufficient to predict the outcome. 95% is for me, above any threshold I would set for saying, yes, this predicts the outcome. That's at least my personal position here. So I would say all of these sets that we're looking at are sufficient for the experience of distress. Then in terms of necessity, and that's actually a harder definition to pin down, but in this case, I would say that either urgency or a motivation to regulate are necessary for the experience of distress, because we see urgency and motivation to regulate present in all of these sets. So just some cool things that we can think about with these approaches. Okay, as we reach the end, and my voice is starting to give out of me, so it's we haven't gotten here just in the nick of time. So one of the motivations here is for actionability, right? We get some pretty good prediction out of these approaches, but prediction wasn't necessarily my motivation. It isn't my motivation right now. My motivation is to try to create models that are actionable, that we have inferences that we can act on, right? So when this happens, and this happens, and this happens, then some outcome of interest is going to occur. And so these methods are aimed at increasing or optimizing our actionability. And in doing that, I want to increase the transparency of our models, right? So I have a whole spiel that I didn't get into here, in comparing this to things like factor models or multiple regression, and models that on the surface of them, on the surface, they seem to give us transparency. Well, what do this factor has, A and B and C. It's like that's what's, but the degree to which a factor can be translated into, again, the world that we see and observe and experience is actually a little bit convoluted, and it's a function of the linear models of each indicator on the latent variable, and the separate regressions, and there's the factor loading, which is akin to the regression weight, and etc. Same thing in a multiple regression. So now I'm actually into my spiel, aren't I? So in a multiple regression, on the surface of it, it seems like a simple representation. We say, oh, well, these predictors predict this outcome, but the way in which we would actually be able to translate that into actionable information in the real world is not really clear, because we're going to estimate regression weights for each of the predictors, and then we're going to multiply the input variables by their weights and then add them up in linear combination and create one set of prediction values through the amalgamation, through the combination of the predictors. All of that I think kind of obscures the relationship between the model and the predictions that it's making and what we might observe in the world. Whereas a set is nicely transparent. It says A and B and C. Or in the case of the sequential information, it was A, and then it's B, and then it's C. And then we can expect the outcome at some level of probability. And so these approaches strike me as both much more actionable than our typical approaches, and also much more transparent. We're also really minimizing assumptions here. So the sets themselves don't encode any interactions or higher order complexity. There's no temporal scaling, there's no lag length, but then also we don't have to be encumbered by that. We don't have to be, yeah, I'm just getting end of the talk brain malfunction. My articulateness is breaking down, but I know the point. The point is this, that when we have a set, all it's really encoding is that the things were present at the same time. And then for the sequences, that they were present, and they were present in a certain order. It's not telling us anything else. Now, thinking about the simplest example of that. So you have set ABC, and it's a combination. It's not a permutation. So there was A and B and C. They occurred together. They may be additive. They may be interactive. They may interact in a simple multiplicative interaction like we use in a regression model. They may interact in some sort of complex dynamical system. They may have feedback. There might be all sorts of different relationships. We don't have to declare them for them to have influence on the response variable, on the dependent variable. Now, that might be unsatisfying. And there might be those of you who are watching this right now and thinking, no, I want to do a computational model. I want to say exactly what the relationships are. Or, hey, you're trashing linear models, but at least if I have a regression model or if I have a VAR model, I have estimates. I have some sense of how one variable relates to another. And sure, I think for me, I just worked with those models enough to be concerned about the degree to which they actually reflect the world around us. And I want to go in the other direction and say, I just want to declare that A and B and C are present. And that's all I want to do. And in their concurrence, in their shared presence, I can show in various different data sets that they have an influence on an outcome. Now, if we can do that in a generalizable and replicable way, and you could say, well, ABC predicted, this outcome in this data set, and then it predicted it in this other data set, and then this other lab tried to do it and they found it. Well, then we can circle back and say, okay, what's the nature of ABC? Is it additive? Is it interactive? If it is interactive, what's the nature of that interaction? I think we can dissociate the work there, right? I think an example that comes to mind is the way that physics separates theoretical work from experimental work, where the theoreticians come up with the ideas and the concepts and the models, and the experimentalists then try to see if they hold up with real world data. Similar kind of division here. I think we can do the work of establishing what the ingredients are without worrying about what the recipe is. Of course, we want the recipe. If we're going to actually cook a delicious meal, in the end, we need that recipe. But we also wouldn't think it's so ridiculous to be sent to the store to just get the ingredients. Just identifying what the ingredients are, I think, has value in itself, especially when you can show that those ingredients actually can influence an outcome. And then you can, again, like I said, circle back and find out the nature of the interactions among the ingredients. Cool, great. We've gotten through this. Now I can post this to YouTube, which is a strange statement because if you're watching it on YouTube. But yeah, I'm glad that I got through this. I'm glad that I could put this up for people to watch. If you're listening to me talk right now, that means you watched the whole thing. And in addition to thanking these 5 folks, thank you for your interest and your attention. And I will see you online. And I have to stop the recording.